Welcome to helpyourmath.com. Today we're going to solve for x. As you can see, this is an exponent problem. So we want to have our base 5 to 2x plus 1 by itself. So I'm just going to divide 3 on both sides. This side cancels out, and this leaves me with 25. Now, as you can see, 25 is a perfect square of 5. So I'm going to have our base same. In order for me to get my base same, I'm going to rewrite 25 as 5 squared, and this side as 2x plus 1 same. I'm just copying the left side. So now my base is same. I can actually solve for my exponents, which is going to give me 2x plus 1, same from here, and this as 2, because 5 squared, which is 25. Now I'm going to subtract 1 from both sides. This side cancels out. This leaves me with 2 minus 1, which is 1. Now, in order for me to get my x by itself, I'm going to divide both sides with 2. And this side cancels out, which leaves me with x equals 1 over 2.
Welcome to helpyourmath.com. In today's video, we're going to be focusing on one-to-one functions and solving for x and logarithmic bases with x variables looking for a solution. So here what we're going to do first for the first problem is use a change of base formula. Here we know we're using change of base because we have an exponential on the 5 here, and we're setting it equal to a 75 with a multiplier outside. Now the work for this is pretty straightforward. So let's take a look at the work for number 1 here on the solve for x. We have 3 on the outside multiplying by 5 to the power of 2x plus 1 on the inside is equivalent to 75. Now here we have a number with a base, and for this to work we have to do what we call a one-to-one on the functions, because when they're one-to-one they have a common base, and those common bases are then evaluated. So let's take a look at the work here. Now, since we're multiplying this base with an exponent here, we want to get rid of this 3 first. And to do that, what we're going to do is divide both sides by 3. In this way, we free ourselves of this 3. This goes away, and we're left with 5 to the power of 2x plus 1. Being equivalent to just 25. 3 quarters make 75 cents, and in the same way, 3 25s make 75. Now we see we have a 5 to the power of 2x plus 1 and a 25. Now the 5 and the 25 are one-to-one because they're common base terms. 5 makes 25 when you expand it to the second power. So the next step here is to take this, just bring it down for the ride, and set it equal to 5 to the second power. Now we have them in what we call one-to-one. Also remembering that whenever we take a log of any base of the same term, this is equivalent to 1, right? So here what we're going to do is we're going to take the log base 5 of each side. And what happens next is the exponents come down with the rule of logs, in which the log of any base of a term with an exponent, the exponent comes to the front of the log with the base and a term. And so here the 2x plus 1 becomes the scalar multiplier in front of the logarithmic term, or in other words the coefficient of the log term. And the 2 is also going to come down in front of this log term. And now this term here becomes 1 because log base 5 of 5, just like log base b of b is 1, log base 5 of 5 is also 1, as well as this log base of 5 being also 1. And so we're left with 2x plus 1 is equal to 2. And this is what we call one-to-one. This is how we work them out. So technically, whenever you see a base to some exponent equal to another base of some exponent, we could just set the exponents equal to each other for this rule. And here we just solve them. So we're moving over the 1. These go away. We get 2x equals 1. And finally, we divide by 2. So we have x is equal to 1/2. Now this is the solution if it works in the system. And it does work because these are exponential terms and they can take all values. So we're done with part 1. Let's move on to part B now. Part 2. Part 2 says log base of 2 of 2x's plus log base of 2 of x plus 3 over 2 is equivalent to 1. And to do this one, we need to know a couple other rules of log. And the only rule we're going to need for this one is log base of some term plus log of the same base of another term is equivalent to the product of those logs under the same base. And here we see we have the plus, we have the common bases, and we have the two terms, so we're going to condense these and multiply the two terms under the new log base 2 of a singular term. And here we're going to use brackets instead of parentheses, and parentheses inside the brackets. And here we see we have the two terms multiplying. Where they were summing before, the terms outside with the log term multiply together here. And so now we're going to use the change of base formula. So we know any log of a base of a term is equal to some solution is interchangeable with the base to the power of the solution being equivalent to the term of the log. And so we're going to use the change of base formula from log form to exponential form and change this logarithmic form to exponential form. So to do that, we take the base of 2, raise it to the power of the solution, which is 1, and set it equal to the log term. We're going to raise this to the power. That gives us 2. Here we're going to distribute this. Gives us 2x squared. 2x's times 3 halves is 2x times 3 is 6x's divided by 2, 3x's. The next step is to subtract the 2 to both sides and make this a quadratic equation. This gives us 0 equals 2x squared plus 3x's minus 2. And now what we need to do is solve this, right? So let me just wipe off some of this stuff since we won't need this over here. You can always rewind this video if you want to see the work that we just did. But as far as the solution for this goes, we're going to have to solve this quadratic. So I needed the space here. So we have 2x squared minus 3x's minus 2 equal to 0. Now there's a few ways we could solve this. But being in a pre-calculus or intermediate algebra class, we could use either quadratic equation, factoring principles, or synthetic division, but here we're going to probably choose factoring, right? And I have a quick little trick that always works for this. So we take the leading coefficient here, put it with 2x in parentheses, both sides, divide this by 2, set this equal to 0. And we're looking for the factors of the master product, which is negative 4, that add up to negative 3. So the factors of negative 4 that add up to negative 3 are going to be negative 4, positive 1, negative 2, positive 2, or negative 1, positive 4. Here we have negative 3, here we have 0, here we have positive 3. So we're looking at these two solutions going into the system, minus 4, positive 1. And here's a cool little trick. We factor out the greatest common factor wherever it exists. Still divided by 2. We get rid of those 2's. We're left with x minus 2. 2x plus 1 equals 0. We solve each case. Here we have plus 2 plus 2. X is 2. One possible solution. Here we subtract 1. We divide by 2. And x equals negative 1/2. Here's another possible solution. For our solution to work in this case, we have to plug it in and hope that the log is not a negative term. When we plug in positive 2 here, this remains positive, this remains positive. Positive 2 works. When we plug in negative 1/2 here, 2 times negative 1/2 is negative 1. For us to take the log of a term, it must be greater or equal, well, greater than 0. And so the log of negative 1/2 will not work. So it's an extraneous root. So we're removing it. The only solution to this problem is x equals 2, because when we insert it into the log terms, we don't have a negative log. And by that, I'll show you the actual work so that you can verify it. So this is the check. And when we check x equals 2, we have log base 2 of 2 times 2 plus log base 2 of 2 plus 3 over 2 equals 1. And then we have the log base 2 of 4 plus the log base 2 of 2 plus 3 halves is 7 halves. So this works because we have two positive logs. So x equals 2 is a solution. When we go to check 1/2, minus 1/2, what we get here is the log base 2 of negative 1/2 times, well, 2 times negative 1/2 plus log base 2 of negative 1/2 plus 3/2 equals 1. And here we have log base 2 of negative 1 plus log base 2 of positive 1. And here we know this does not exist. So this is also 0. And we know this is not a possible solution because the log of anything of 1 is 0. And you can't take the log of a negative 1. It's negative infinity. So this does not work. So x to the negative 1/2 is not a solution and only the positive 2 is. Thank you.